So I changed the title to Plunder instead of Plan, just to kind of better reflect what's what here, but it's the same talk, I promise. So my name is Jack, and I'm working for Vaporware, which is like, we did not create this technology. We're using it and we think it's great, and like I know a fair bit about it, but it's like, if you have very advanced questions, I might not be the person to talk to, but like the person who is the right person to talk to is here. So we'll arrange that in that case. So I struggled a bit coming up with the right angle for this talk, because you can come at it from a few different perspectives. Because what this technology is doing is that it's kind of advocating for a paradigm shift. It's a different way of looking at a problem, which means that you kind of have to step away from the systems that you're used to working with and the problems that you think that you want to solve, at least temporarily, and then kind of like once you have the whole picture, then you can see whether it actually makes sense or not. Maybe it doesn't. So the unifying goal is to give you back control over your own computing. Should apparently not do that. So the current software ecosystem is extremely complicated and changes constantly, and it's a black box that you can never really understand. We want you to be able to understand and to master every aspect of your computer system. We want to make it actually realistic to keep your environment under tighter control, to make it more understandable and predictable. And to do this, we're kind of coming at this from two directions. So one is to basically expand the domain that functional programming is useful in. So lots of people here are functional programmers, and we kind of intuitively get the power of immutability and pure functions and how this can be used to reduce complexity. But one problem with functional languages today is that your program is still going to run in a stateful environment. So the advantages that you get from working in a very safe or pure or typed language are limited to a very small part of the system that you actually care about at the end of the day. Because at the end of the day, hardware is stateful, and the only hardware device that you can really affect in a pure way is memory and CPU. So the aim here is to bring more of the statefulness under the control of pure functions. So if you can fit your whole digital life into one single unified system and use typed functional programming everywhere, then that gives you a lot more control. So the second angle is that we want to ensure a robust and understandable software supply chain. It doesn't matter how secure or pure or typed your language is if code that you're depending on can do all of this other crap, and it might even change from underneath your feet. So if we can ensure that you don't have to rely on a huge complex ball of mud of code in order to get anything done, then, well, programs become much easier to understand. Because if you show me a 10-line program that depends on 10,000 lines of libraries, well, then I can show you a 10,000 10-line program. So what I'm going to do is that I will first look very briefly at the architecture of this system. And then we'll have this kind of back and forth kind of structure where I'll first show you a demo or like an example of something, and then I'll explain how and why that works. And then we'll go back to a new problem and like go back and forth, well, 3 times. And then I'll try to tie that together into like a bigger vision, talk about that and how we hope and believe that this system will continue to evolve. But just a note, I'm not going to go that deep into technical details. So like, I want you to see the big picture, like the why, basically. If you want detail, there is documentation available online, and like I and Ben and like all the other ones involved in this are happy to talk about it afterwards. So, Plan, which my talk was originally titled, is part of a computing system called Plunder. So Plunder is named in the same tradition as Scheme and Racket, so it's a Lisp system in some ways, and it consists of a few different components. So at the bottom you have Plan, which is both the data model and the evaluation model. And to the left there you have kind of like a language side, rex is a syntax, which we're not going to talk about. You'll see it, but I'm not going to explain it. And sire, which is the actual user-facing language. And then on the other side, you have stuff that makes this useful as a VM. And we're not going to talk about most of this. We're just going to focus on plan and sire. You're going to see rex, and we're going to kind of hand wave the syscalls bit a bit like towards the end, just to when I'm discussing the kind of motivations and like bigger picture. But most of the time is going to be spent on plan and sire. So that's a small overview, and let's just start looking at the two problems, like angles that we talked about. So yeah, let's just start looking at an example. Is my cursor there? Cool, nice. So let's say that we wanted to write a simple to-do list app. And is this big enough? Cool, nice. So here's an example in Haskell. Very simple. It's like we have a type, which is just a list of items and whether they are done or not. We have a way of showing those, and like we can add new items to the list, and we can delete them. And we have a step function down here in the state monad, which just like it takes, it does parsing and updating in the same step, just because like simple small example. But it's like it parses, and based on the input, it's going to do one of these actions. And then we hook that up into a kind of harness down here to actually do I/O and loop and so on. So like this is really just one step, hence the name. So just quickly here, you see how much the types actually give you. Like there's really nothing that most of this code can do beyond what it's supposed to do. So like you really have total control, well, almost total control over like what the different components are usable for. So it would be really nice if we could bring like our entire computing experience into this paradigm. So let's see how this works. So we enter the main loop, and then we can add, we need to wash. Well, that failed. Add clean. We can say that we're done washing, and because of that, we also want to delete it. Very simple, like nothing surprising there, hopefully. Problem is, if we exit this and then enter that again, that like the list is gone. So like we only have our new items here, which is not like a great to-do list because it's used for remembering things. So let's make this persistent. So we take this code and we go to ChatGPT. And because it's, I mean, we could just do this with a text file, but since we want this to actually scale, we're going to use Postgres. We paste that, and we get a response, hopefully. Maybe. Oh, did I? Oh, okay. So I haven't been able to connect to the Wi-Fi, so I'm using my phone, which probably shut down the hotspot. Oh, wait a second.
I just saw Wi-Fi.
Okay, cool. Nice. So is this? No, it's still just, no. Why is my iPhone not there? Yeah, but it has been working for me. Let's see if this. well, still not? Okay, give me a second here, I'll fix this. Easier to do down here. Okay, there's my iPhone, perfect. Refresh, okay. There we go. So we need a database connection. Yeah, we need to change the code as well. I mean, okay, lots of that. Okay, we need a, yeah, we have to actually splice in code here, which we can't even check the syntax of. New functions for each one of the operations. So if we add, yeah, like fuck this. So let's just be good functional programmers and say that this is a toy example and move on to the next interesting problem. I mean, that's a joke, but it's, it shows that there's a fundamental kind of impedance mismatch between how functional programming languages work and like what we actually want them to do in the end. So since the language is good, or at least so I presume today, what if we instead redesign the system that we use it in? What if we instead just serialized this main closure instead of doing any of that other crap? So I'm not going to show you a bit of Sire, and you're not going to recognize the syntax, so don't freak out. But it's basically a direct port of the Haskell. And sorry, I don't got syntax highlighting working. We can see here. It's very similar. So you have, I mean, it's untyped, so we don't have a type definition, but we have a way of showing. We have a way of adding, deleting, done. The only thing that's really different here is the step function. Because it's, so like this equals sign here is like just definition, let binding, then we're switching based on the command. New let binding, so we're adding the item to the state using the function up there. And then we're returning a tuple with the printed state and the step function partially applied to the new state. So like we're recursing with using the new state. So we're returning a partially applied function, and then we're just giving that the empty list in the main function. So it's slightly different. We don't have the state mode. Like the way that we do I/O is different, basically, and the thing that this step function is returning is different. So let's just see how this works. So we're going to save this. And then we're going to use this to get a prompt, which is there. And now we can add run, add wash, add clean, done wash, and we don't want to run. Cool. And we exit and we enter it again, and we, well, I actually added a show command there so we can do this, and we see that we still have our previous state. Cool, nice. So, what this step function is that it's a transition function. It's a function that takes a state and an input and gives you back an output and a function that is waiting to be applied to the next input. And in main, we just tell our transition function which its starting state should be. So this can be made trivially persistent by simply saving all the inputs to a log. And because our language is purely functional, we know that running our transition function on all the inputs of that log, again, will get us back to the same state. And of course, we can take a snapshot of this, and so we don't have to recompute it from the log every time. A bunch of optimizations are possible. And we have a language runtime that knows about this and does that work for you. So notice that this is basically a database engine, where you create databases by writing functions. So we've just removed the impedance mismatch that we encountered earlier. You get an ACID database for free just by virtue of writing a functional program. But what is this current state that we're storing snapshots of? Well, it's this partially applied function here. Step state is a partially applied transition function that knows what its current state is and is just waiting for the next input. That's the snapshot that we need to store. Okay. I go back here. Cool, nice. But how do you store a partially applied function? Well, you have the lambda calculus, which I presume that people here are aware of, given the name. And the lambda calculus is technically it is a well-known formalism for functions. And technically, you can definitely look at it like a data structure. You could represent it like this, and that's like an example lambda term there. Like it's the identity function applied to a symbol y. And you have the same thing there, but in a syntax tree variant. And if you know that x should be bound to the value 5, then you can just go in and substitute x in the expression. The problem is that if the body of that function is really big and maybe uses x several times, doing that substitution will be needlessly wasteful because you might not even need all those. And it's like you have to, like if there are functions there and bound names, you have to make sure that they don't collide, all that stuff. So what people usually do is that you have some sort of environment which keep tracks of bound names. Problem is that then we've introduced implicit state. We can't just take that syntax tree like lambda, y, big body and write that to disk because like there's information that we don't know about. We've lost it. So when you're implementing the lambda calculus, you need to choose some way of implementing the environment and like closures. And in most cases, this is like completely abstract. There's nothing in the model that specifies how that should look. So there are a number of ways you can choose. There are probably more, but here are a few. So you can choose one of these when you're implementing closures. We're not going to talk about most of those because like they're not relevant for us. But remember, like we're building a database engine here, so we want the representation that is easy to serialize because we're writing closures to and from disk all the time. So ideally, the in-memory representation of a closure is just an ADT, at least formally. Then you can optimize with pointers and deduplicate and all that. But formally, it should just be a syntax tree. So most of these ways of implementing closures rely on specifics of the runtime system's memory management. And so like, they're relatively difficult to serialize. So the only ones that are really relevant for us are the top two, lambda lifting and closure conversion. And they're very similar to each other, so we can actually trivially support both. Both of them just represent the environment by explicitly passing it to a function, either as a record or as a bunch of extra arguments, so curried or not, basically. So in both of these paradigms, a closure is simply a function without any free variables that has been partially applied to some of its arguments. And we require that recursively. All functions, or rather, no functions can have free variables. So if a nested function requires a variable or a value from its surrounding context, it needs to be explicitly inwards or downwards, however you want to see it. So this means that there is no environment that you can rip a function out of. Everything is already there, so you can just write it to disk as is. So there's a name for this kind of function without free variables. It's called a supercombinator. Loosely speaking, that's just what I said. It's a function without free variables. there's a more fancy definition that we don't need to get into at the moment because it requires a definition of a combinator. But I mean, it's just a function without free variables or a constant, recursively non-free. So they're very common. GHC uses them internally, and they're fast to compile to, and they're very well suited to graph reduction evaluation. So what we've done is very simple. We have a data structure for supercombinators that is as minimal as possible, it's easy to lay out efficiently in memory, and it's human readable. That's it. So it's called plan, and formally it looks like this. It's probably not obvious what this means without looking at semantics, but for now I'm just going to spoil that this is a Merkle DAG of supercombinators. We'll look at that in more detail later, but for now just look at the third case here. So we call it app for application. So f app applied to x is a partially applied function. If f has arity 1, then it will reduce to something. Otherwise, it's just kept as a tuple. And that is what a closure is here. And again, we'll return to this later. But for now, let's just make clear that this is the whole data model of our system. So at the base level, we require all code and data to be represented as this data structure. It's supercombinators all the way down. And that's at the end of the day. And remember, there's nothing strange going on here. This is old technology. GHC uses this internally, and there's this cool paper from 1982 which shows how they're useful for implementing applicative functional languages. So the only thing that's new here is that we've made this forwards and backwards compatible so that we can use this as an actual database format. And we allow this data structure to cut through the entire system. We'll return to that. Okay, so let's take a step back. That might seem abstract, and it kind of is, but remember the to-do list app I showed you. It was automatically persisted because we can just serialize the closure of the main loop. So this is the data structure that allows us to do this. This is the data structure that is stored both in memory during execution and on disk. So we have a system where everything agrees on this one particular way to represent closures, and we've made sure that it's fast to work with in memory, and that it's fast to compile to, and that it's easy to map back and forth between memory and disk, and that you can inspect, deconstruct, and construct it from inside the system. So the Lambda calculus is originally a very abstract system, at least in practice. But using supercombinators, we've turned it into a very concrete system where there's no magic going on behind the scenes. Nothing is abstract and everything is concrete, and closures aren't just an implementation detail, they're actually first-class objects that can be manipulated and inspected inside the system. Okay, so that's one angle. By storing closures, we get a purely functional database, which you can program by just writing normal functional programs. So if we move back to use cases and motivations, we wanted to provide alternative ways of solving these two problems. Stateful functional programming, or bringing stateful programming under the control of functional programming, and the software supply chain. So we've already seen how we can sidestep the need to write things to disk. You could see how that can be used to implement, for example, microservices. It doesn't have, the input doesn't have to come from a terminal. It could come from a network. Same thing with the output. It could be sent to someone else. And it's all automatically persisted. There's a bit more to say there, since disk is not the only hardware you actually want to have control over, and we'll return to that towards the end because it's actually not done. But let's look at the second one for now. So let me just start a process here while we're waiting. I think it's this one. Yeah, it is. Cool. So what is it? It's this. Nice. That's going. Now, please forget everything I said about this being a database. Instead, look at this as a virtual machine, or like a language platform. So you've already seen the data model of plan, which is how all code and data in the system are represented. I didn't tell you about the semantics, but this is the entire spec of plan. Now, just a few points here. We're not going to talk about this in detail. There is documentation available online for those who want it. But it's basically just a lambda calculus, but we only substitute once the function is fully saturated, roughly. You never actually have to use this if you're programming in the system. Like, this is for you, the kind of people who are here. But there is documentation available online if you want it. Anyway, this specification can actually be more or less directly translated into like C or Rust or Python and still be fairly performant. So like any moderately advanced computer science student can do it. Like, they might not understand exactly what they're doing, but they can do it. So like a minimal, reasonably performant Haskell implementation is 54 lines of code. We have a realistic C implementation on 3,000 lines of code, including a big num library. And that's without dependencies, by the way. Let's have let's do this first, yeah. And then Sire, the kind of Lispy Haskell, which I haven't told you that much about. Its compiler is just 2,000 lines of code in Sire. And that might sound circular, and it is. So like, if Sire is written Sire, how do you then get it to run? Well, we have a compiled version of the Sire compiler, and that's like 20 kilobytes of plan. And you can feed that into the runtime system. And that's what I started in the background. Let's check on that. Like, it's still going, OK. So like, we're loading the Sire compiler from a file of serialized plan. While that's going, let's have a look here. Oh, it's done. Cool. So for example, we can fold a list, or an array, actually. Cool. We could do more advanced examples, but let's not, especially since I wasted time on the Wi-Fi. But we can see here, so we can check. Right, so here are let's actually make that human readable. Right, so we have, that's the binary that's been compiled, and then we have the big num libraries. Actually, it's better if we just check the line count. So basically here, big num library, the actual plan runtime, compiled version of Sire, so that's Sire in plan, and here's Sire in Sire, and here's some printing stuff. So if we check how big the runtime is, what did I?
You need a comment.
Oh, right, of course, thank you. There we go. Cool. So that's 3,000 lines of C. Most of it, I was going to say something wrong. So most of it is actually like in here, which is the interesting part. Then we have a bunch in here, which probably can be compressed or emitted. We'll see how that goes. But like, it's small, no dependencies either. We can check how big the Sire is, 2,100 lines. And let's check how many bytes that are in the compiled Sire. Right, tar. Yeah, so 20 kilobytes, roughly. So this might sound like you have to trust our compiled Sire file here. But the thing is this reading compiled plan is actually very, very doable. So like, it's been designed to be easy for humans to read. So here's an example of how the fold right function that we just used looks in plan. Since you're not used to reading serialized plan, you won't get all the details here. but like we can still make out a few things. So we have the not function, which takes an argument and does an if on it. And if it's true, then it returns false. Otherwise, it returns true. We have the identity function, which just takes an argument and gives it back. Many of the other ones uses they use primitive opcodes of plan. So like the 2 there, for example, or the 1 here, they are actually built-in operators. So once you understand plan, those are very, very straightforward to read. We're not going to go into that now. Anyway, the point here is that any programmer can follow these 4 steps to get to basically arbitrary language functionality. So you implement the plan spec. You inspect the Sire in plan code by comparing that visually to the Sire in Sire code. Then you load the Sire compiler, feed that to the runtime like we did. Then you can extend Sire with macros, so you can recompile Sire again using its own compiler. You can write new compilers using Sire, and you name it. Of course, you don't have to do this. I mean, you do have to do the number 3, maybe. Yeah, I recommend number 4 as well. You can just use our runtime, and you can trust our compiled Sire. But you can. Like, you don't have to trust us. Because once you have a plan runtime, nowhere in this chain do you trust a binary. You can always build the compiler from source. You don't need the binary for the previous version. The closest thing that we have to a compiler binary is the plan expression that codes for the Sire compiler. And as I showed you, this is significantly more readable than normal binary code. The plan is designed, again, to be human understandable. So you do have to trust the language that you're implementing plan in. But this can be any language. We don't depend on any particular one. We have the spec, and then it's up to you to implement it if you don't want to use ours. So while you do need some amount of trust, you can limit it to a very small part of the system. And you can also choose to use a component there that you trust, that is very unlikely to be compromised. For example, GCC. So in this way, we addressed the trusting trust problem in a limited but still important way. And for those who don't know, the trusting trust problem is that if you rely on compiler binaries, they can actually contain malicious code that the compiler replicates every time it recompiles itself. But since there are no binaries here, we don't have that. And again, you don't have to do this. It's for nerds and people with extreme security requirements. So hopefully you agree that this is nice in principle. But how practical is it to use? Is it fast? Does it scale? Let's actually have a look at how our runtime is in practice. So demo again. Next, number 5 this time. Oh, wait, wrong screen. There we go. There we go. So this is just a simple demo web application. There are 70 gigabytes of images of My Little Pony. Not because I am that into that, but we have another guy who is, and they're very good as a data set because they're very autistically tagged. So, Shai is the name, right? Yeah. I don't remember the other tags. Sparkle or something? Yeah. OK, so there's just one image with that combination. Anyway, as you can see, we actually reject invalid tags in red if they don't exist. And from the inside of the system, this is just one value. There's 70 gigabytes of images, and we can transparently page them in and out, like between memory and disk. And this is just like, this is using the naive prototype in Haskell. We've been prototyping in Haskell since it's much faster to iterate. But now that the spec is stable, we switch to C. You saw the C runtime in action earlier. That's not feature complete yet, which is why we're using Haskell here. But this 1 million data set, 1 million images data set, 70 gigabytes actually looks like one inspectable value from the inside of the system, even though I only have 32 gigabytes of memory on this machine. Okay, so how did this work? Let's look at our data model again. So we can see that the first case here appears redundant. Like, why would you want to store a plan inside of another plan? So this is called a pin, which is basically a hint to the runtime system so that it can optimize its memory layout. It's a magic box that's saying that anything inside this box belongs together and should be stored in a contiguous region, both in memory and on disk. And this allows us to make efficient use of the CPU cache. It's also used for deduplication. So identical pins never occur twice in the state tree. The state tree is actually a DAG, and pins are merge nodes. And in practice, if I expect to compare a value for equality many, many times, well, the fastest way to do that is to just hash it the first time, keep that around, and like if I in the future hash to the same value again, then I just remove that and point to the previous one that I already had. So this is why this is a Merkle DAG of pins of super combinators, but we haven't gotten to that part. And the merge nodes are always content addressable by their hash, which is always pre-computed. So the second case here that we call law, that's just a user-defined function, user-defined super combinator. So it has a name, which is a string encoded as a natural number. And it has a number of arguments before which, it needs that many arguments before it can reduce. And then it has a body, which is another plan value, and we can encode code using plan as well. And then the fourth case is just a natural number, arbitrary size. And these can be used as data, but some of them are also built-in functions. And the third case is, as we saw before, is function application. So we already looked a little bit at this. They're really just tuples, but if f is saturated, then it reduces. So let's look a little bit deeper at how they work in practice. So say that we wanted to apply this law here, i.e. a user-defined function, that takes 4 arguments to, 4 arguments. So we do that here in nested apps. And since all functions are super combinators, we know that foo won't ever access any values except for 0, 1, 2, and 3. So the environment that we have to pass it during execution is always completely explicit. We always know the size, which means that we can simply pass the environment on the stack. We don't have to use an association list or a symbol table or a linked list or anything like that. We can compare this to eval apply from Lisp. Eval there needs to dereference names. And that runs in linear time since the environment is an association list. But here, dereferencing variables actually runs in constant time because the environment size is already known and can be passed on the stack. So in practice, the runtime data structure the runtime can use this data structure instead of the formal one when you're inspecting values. So as you can see, this is very similar to the formal one. Like the pin, law, and NAT cases are exactly the same. The app case has been optimized to keep around an array of the values that we have already been given, which means that we can lay out all the plan values completely linearly in memory. We don't have to pointer chase our way through nested app nodes. We might still have to actually pointer chase like when we're going in reading arguments, but we will have to do that anyway. So even though it feels like a very formal, pure, syntax-oriented system from the inside, you're essentially manipulating memory directly. Because we've allowed this structure of closures to cut through the entire system, from the runtime to the high-level language, you can actually as a very pure functional programmer, directly affect how the machine operates and how it lays out its data. So everything I talked about so far already exists. Now let's spend a little bit of time talking about the future. Like, why did we build this? Where do we want to go with it? So this part is going to be a bit more hand-wavy, naturally, since it doesn't exist. But I want to give you a sense of what the idea here is. So on a high level, we want to make it possible for people to write their own small scripts and applications again. This used to be possible with PCs, especially Unix kind of revolutionized this. But as soon as you want to do anything with networking, it's this huge complexity explosion. Like, if I want to send a message to one of my friends, how do I do that? I need the IP of his current device, which can actually change minute by minute. And even worse, I might be switching between my phone and my laptop. And in this day and age, I expect my code and data to be available on both. So what we're aiming for here is to bring back the old Unix experience where you're actually in control of your computing while keeping the conveniences of the cloud. And this might sound political, and like if you understand politics broadly enough, it definitely is. But it's also just about like reliability and security. So if your software has to talk to some cloud service to even work, it's simply going to be more fragile. In some cases, that's worth it. It's not that servers are fundamentally bad, but it would be nice if we could reduce the set of tasks that you need them for. So, but the problem is, like, none of this that I showed you today really solves that. So, like, what's up? Why did we build this crap? Well, if I want to be able to access my code and data on any device, it would be really convenient if I had a universal format for representing code and data. And it would be extra convenient if that code and data was natively content addressable, so that even if though my phone logically has my whole state, it can download code and data on demand by noticing as, oh, I'm looking for a value here, which I know the hash of. Let's try to fetch that. And we'll always be able to know whether it actually got the correct value or not. But logically, it should just be the same program that is running on my laptop. So we saw that in the My Little Pony demo, where all the values were stored inside a single state tree, but were transparently mapped back and forth between memory and disk. We want the same thing to happen between disk, like memory, disk, cloud. And of course, there's still some stuff which that doesn't deal with. So like, I talked about sending a message to a friend. I haven't shown you anything that would make that simpler. The problem is that if we're adding the ability to interact with a networking interface, well, then that could actually change with time and between devices. So this universal format for code and data might actually turn completely useless. Like, you have the code, but it doesn't do anything useful. It would be coupled to particular hardware. So we need some sort of abstract notion of sending a network message, which would be guaranteed not to change, even though the way it's implemented could look very different in the future or just on different devices. Because the idea here is that instead of directly affecting the hardware, you would store a request to affect the hardware in your main closure. And then you also have a continuation function that gets triggered once that's actually finished. So the person, like the runtime, the environment that is running your closure for you, can take that request and map that onto some sort of real hardware operation. So we need to standardize some sort of logical I/O device, which I can use from inside the system to send a message of some sort to some sort of address, which isn't just an IP address. And we want that for a few other hardware interfaces as well. So like we want to be able to query the system for the current time, for example. We want to display a piece of data to the user. We don't want to say how that happens. We don't want to, like just because I say logical, don't think of neat abstractions. Like we don't want sockets here, for example. We want to abstract away the details of the mechanics, but not of the semantics. And there's a way for this way of interacting with hardware. It's called an exokernel. And we intend for our runtime to essentially be an exokernel that offers a way for code inside the system to interact with logical hardware devices directly. So that is our vision. Inside the system, we want to use those logical hardware interfaces to build an operating system that is actually adapted to the modern network setting. And we think that we can do much better than what already exists. But you can also just have independent applications which run directly against this exokernel, in which case that application never has the bit rot. Like once you have the code, it will work. Even if our OS changes, that code is completely independent from that. And even code inside our system, like it might bit rot, but we think that it will do so much slower because we're separating mechanics from semantics, and we also believe that it will be much more understandable because you get so much more out of the box. So we don't have to live like this. A better way is possible. Okay. Is that because I'm done? No. Okay, cool. Okay, nice. That was, I mean, perfect timing. So like, if you find this compelling, here are a few ways to get in touch and get started. And thank you.